Okay, welcome to the second part of topic 4 in Unisa PYC3704. We're going from bottom of page 102 to the end on page 107. And we have our water wings on. We're swimming over deep water, but we have our water wings on and we're wearing and we're on a lilo. So don't worry, we don't have to understand the deep stuff yet. We're going to start at the end. And this is like, I don't know how many times I've tried to do this. I keep accidentally splishing into the deep water and then not knowing what's going on and having to start again. All right. So what we're going to be able to do by the end of this topic is calculate the Z statistic, which we already know how to do from topic 3, okay? This is for single groups design the Z X bar to test a hypothesis when the population standard deviation sigma is known, number 1. Number 2, calculate and use the T statistic, which will be T X bar, for single groups design to test a hypothesis when the population standard deviation sigma is unknown. And we can also use this for smaller samples, smaller than 30, okay? Finally, we're going to determine whether or not to reject the null hypothesis using a decision rule, which is again something we already did in topic 3. So don't worry, don't be daunted, and just don't jump off the lilo, okay? Except for fun, if you've got lots of extra time. Because if you jump off the lilo, you discover the water's much deeper than you thought. Okay, let me just show that to you in the book. It's at the end of page 107. Let me share from now on. Okay, here we go. Okay, so we want to be able to use Z for Zx bar, from which we'll get our p-value and see whether it's greater than or less than our alpha value. In other words, whether the result of our sample test and results are statistically significant or not, whether we can reject the null hypothesis or not. Then we're going to do the same thing using the T statistics, okay, to see whether we can reject the null hypothesis or not again. So test the hypothesis, in other words, check whether we can reject the null hypothesis when we don't know the population standard deviation, okay? And then thirdly, we're going to know about the decision rule, which is the name of something we've already learned what to do, okay? And that is basically this, okay? Oh, example decision rule for two-tailed. Oh my Lord, you see, it is the deep end. Okay, now, I actually even forgot this. So let's, before we do anything else, oopsie, where's it gone? Here we go. This. Remember, keep this in your head. You're going to get befuddled later if you're anything like me. When to reject the null hypothesis in hypothesis testing. This is based on the p-value and the chosen significance level, alpha. If the p-value is less than alpha, we reject the null hypothesis. The result is statistically significant. There is strong evidence against the null hypothesis, suggesting the sample mean is significantly different from the population mean. Okay, if the p-value is greater than alpha, we fail to reject the null hypothesis. The result is not statistically significant. There is not enough evidence to conclude a difference from the population mean. So why is it that a smaller value means that we reject the result? You'd think that a bigger value would cause you to reject the result. That's because the p-value is opposite to the z value and it's opposite to the t-value. So let's just scoot over to our Excel spreadsheet for a second so we can conceptualize this visually. Remember this graph here, okay? If you're looking at this as a test statistic, your Z value, this is your Z axis, is going to be on this line. It's measuring this area. So the bigger your Z value, the smaller your p-value. Your p-value is over here and over here. These little 0.05s, little 0.05 over here. That's where your p-value is. So the bigger your Z value, the smaller your p-value. So a smaller p-value means, yo, this is very accurate. It covers all our bases. It's statistically significant. Okay? Oops. Oh, what have I wrought? Okay. Right. So those things now said, let's go back to the beginning of the story. And we're going to go back to page 102 in the book. And then hopefully work our way through successfully to the end. I think we will. It's pretty simple, actually, if we keep our water wings on and we don't jump off the ladder. We are testing a single mean where the population standard deviation is unknown. Okay, so we don't normally know population standard deviations. It's unusual. So the Z-test cannot be used reliably. Now, the results of the t-test and the Z-test are very close. They're very, very similar. So if you don't know the population standard deviation and you just use the Z-test, you've actually got a good chance of getting the right answer. And the other thing is that the t-test is inherently less certain than the Z-test. It's an approximation. It's a measurement of more or less how confident we are. And what are we going to accept and what are we going to reject? More or less approximately. So that's all we need to know about that as a big picture. We're not diving into that water. Okay. Right, so now we're going to scoot over and look at how we do it in exactly the same way for the t-test as we do it on the z-test. Okay, let me explain the experiment we're working with before we do that. Okay, so for the example that's used is we want to know if very anxious PYC3704 students do worse in the exams than the general student population or not. So we say, oh, over the years, the average grade for most students in this course is 60%. So let's see who's very anxious. Let's get everyone to fill out a questionnaire, and we'll say that the people on the extreme side, like 7, if they get a 7, an 8, or a 9, in our ordinal scale of how anxious do you feel, what are your symptoms, what are your behaviors, those people that score way on that side of the bell curve, they're the people we're going to test. And we get a sample of 25 for our most anxious students. So our N is 25. And they have a standard deviation of 15, all right? Which is quite a wide range, right? Of grades. So now we've got all the numbers we need to get our t value. And from that, our p value. So our t value is the same as the z value. Okay, it's the same numbers, it's just that here we're working with samples instead of population because we don't actually have the information for population. So our t value is, or our t statistic, same, written in the same way as the z statistic, as tx bar is the average, the mean of the sample minus the mean of the population, just like the z statistic, over our standard error. And here, instead of writing this with a sigma, we write it with an S because we write standard deviation with sigma for population and S for sample. Okay. And the formula is exactly the same. So page 105, our standard error is x bar, is our standard deviation for the sample over the square root of n. Okay, great. Oh, one other thing. Before this, there's something called DF. DF stands for, what does DF stand for, everyone? I've forgotten already. And I've been looking at it in depth. Deep end again. DF is, degree of is DF. G, I've forgotten what DF is. Here we go. Degrees of freedom. And degrees of freedom means how many subjects do we have? How many pieces of information? In this case, it's one sample. So we work out degrees of freedom as n minus 1. So instead of 20, because we've got 25 students in our sample, degrees of freedom, DF, is going to be 24. Okay, so that's easy to remember. And we'll come across n minus 1. Whenever we work things out using a sample instead of a population, we say n minus 1 because the mathematical guys have found that you get a closer number to the truth if you take a minus 1 with your n, because otherwise it just tends to be out by approximately that much. Okay, so that's an interesting thing. It's practically a constant. It's very interesting, but that's deep end again. We don't want to be diving. All right, so back to our little formula. So we've got our standard error, which is going to be 20, it's going to be 15 is our standard deviation for a sample of 25 students. Square root of 25, look how small the number is. It's smaller than 30. That means we use a t-test. Okay, another reason to use a t-test. So t-test is less certain than a z-score. And it gives you a slightly different number as well. So now we do all the math, we plug it in to that formula. Okay, so our t-score is x bar minus mu over s over the square root of n. So x bar is 55, mu, population mean is 60, over the standard deviation of 15 over the square root of 25, which is minus 5 over 3, which is minus 1.667. Okay, great. So that's our t statistic or t value, 1.667. And if we were looking at a graph, we would be looking at, where's my Excel gone? Ah, never mind. We would be looking at that distance from the mean is 1.667. That's what we're looking at, okay? To our standard deviation. Now we're going to work out our p-value. Now, because it's a t, we actually do this with Excel. And I have put this into a screenshot so that it's big enough to see. So in Excel, you go to the function bar and you find the t-dist function. If you forget what this is, you can look it up on the internet, easy peasy. Okay? Here, you're going to put in your t value. Let me put this in as text. This is your t value. That we just got from that formula, the tx bar, right? I'm just going to write it like this. All right, degree of freedom is n minus 1. All right, so that's easy. Tails, here it's just less than or greater than. So if it's one tail, There's your answer. You can see there's a little typo in the book. It should be 0.0539, blah, 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 but you can round to 0.54. So on page 105, you might want to, if you wish to have certainty, correct the textbook so that it says 0.54 instead of 0.55 as the roundings. Okay, now look what happens if there's two tails. Look how simple this is. You change that to 2. Okay, this is actually an image, right? Change that to 2, that'll change automatically to 0.1, dum da dum da dum da dum da dum da dum. Okay, so that's how you get your p-value in a t-test with Excel. Now, you can look it up in a t-table, which I found far too much deep end, because then it's a whole different way of looking at the numbers. And you can get an approximation on the Z table. So let me just, which I discovered thanks to my tutor ChatGPT. Here we go. If you take 1.67 as your t-value, in a large, what's this, degree of freedom, if your n number is big, then your t-score is going to be approximately your z-score anyway. Then you go to your z-table and you find your p-value for if z is greater than 1.67, right? And you find, oh, it's approximately 0.475, which is very close to our t-score, right? Our p-value from the t-score, which was 0.54. So it's not far off. It's like 1% difference, okay? And the bigger n, the closer those two numbers get. But this is less certain than our z-score. It's more of a fuzz. It's not that exact, okay? If it's a two-tailed test, multiply by 2. All right. So now, let's just scoot back to the book before we accidentally land in deep water again. Okay, so we've got P as 0.55. So this is not less than our alpha level of 0.05. So we cannot reject the null hypothesis. There's no statistical significance to this sample. There's no evidence to show that very anxious students do worse in the exams. Yay! All right. Now, there's a few provisos. Let me just get rid of my little annotations here. There we go. There's a few provisos. Oopsie. There we go. There's the decision rule. The decision rule is, and this we're definitely going to have to memorize for the exams. If the p-value is equal to or less than, okay, little Pac-Man with the wide side to the right, which is opposite. Let me annotate. If the p-value is equal to or less than the chosen significance level alpha, reject the null hypothesis in favor of H1. In other words, our little threshold on that bell curve is the tiny little bits on the edge of the tail, and those are smaller than 5%, okay? Then we can reject our null hypothesis and go, wow, our research is a success. Yay, we're proving our hypothesis is probably true. We've got supporting evidence for our hypothesis, okay? Now here, because p-value being equal to 0.055 is not equal to and less or less than, okay, that's not true. It's not equal to or less than alpha. Do not reject the null hypothesis in favor of the alternative hypothesis. There we go. That's the decision rule. So it's actually very simple. You just got to put it in your head so that when you're focusing the exams, it doesn't take a lot of cognitive load to remember this stuff. You have to learn it like a language through repetition and memorizing, okay? but we've got it, we've grasped it. Now, there's another issue. Say we do our thing and we find, oh, our very anxious students are also our stars. They have averaged 65. Our computed sample mean is 65. So then our alternative hypothesis cannot be true. Okay, it can't possibly be true. It's never going to be possible. It cannot be smaller than 60. So there's no point in doing all of these mathematical things. You go, oh, this is actually bigger than average. So we know before we do any calculations at all that we cannot reject the null hypothesis. And watch out for this, because you don't want to make a mistake, forget this, and do a ton of work and then not get your grade. Okay. Or mess up a real life experiment. So let's see. I think that is it. Excel now gives us a choice of one-tailed and two-tailed, so we don't have to think about that. And here is a bit of deep swimming, which we're going to skip over. And that is the end of this video. I really hope it helps, and I really hope it's helped to make it simple and learnable. Okay, I'm going to go and do all the problems now and see whether I've grasped this correctly or not. Good luck. See you in the next video in topic 5.